We're recording, so welcome. So before we start, I will do a quick recap of what we did last lecture, and just focusing on the shear center and the calculation, what we did to get the shear center. So skipping forward to the slides a bit. So yeah, we said the shear center is basically the location at which we can apply a force to it, and then our structure just purely bends, and we don't see any twisting or coupling between twisting and bending. And what we do to find that shear center, like for a symmetrical beam, especially when it's double symmetric, it's easy to find because then it's located at the axis of symmetry, at the cross section of the two axes of symmetry. But then you have to have two axes of symmetry. If you have one axis of symmetry, you also probably know, you can guess that the shear center will lie on that axis, but you still have to figure out the x or y component depending on where you have the symmetry. So if you want to find the location of the shear center, what we do is a moment equivalence study. So we say the moments created by the shear force around the point X or point O must be equal to the moments created by the shear flows around that same point. And we also said, like, if we have a cross section, say if you have where all the shear flows in the cross section goes to that intersection, then the shear center automatically lies on that point. Because again, what we said is when I find how we determine the shear center is based on the moment equation, moment equivalence equation. So if you actually take the moments around that intersection, then automatically the equation will be satisfied. So whenever you have an intersection between shear lines, that's where your shear center lies automatically. You don't have to do any calculations. The question becomes like, okay, what if we have a C-section? So we now don't have an intersection between the shear flows. At least we don't have one point in which all the shear centers or shear flows intersect. So we can state, for example, at point 2, the shear flow in 1, 2, and 2, 3 intersect, but then you still have the shear flow in point 3, 4, and then coincidentally you can choose other points that at least 2 of them intersect, but 1 of them doesn't intersect. So what we did here is for this C section, we reduced our equation for the shear flow significantly. So we have Sy Ixx 0 to S T Ty ds. So the Sy is our shear force, that's applied shear force. The Ixx are moment of inertia. So in this case, we only have to calculate Ixx. So we did that, and based on that, we calculate the shear flows in 1, 2. And we don't even calculate the shear flow in, say, 0.23, because we say, well, we take the intersection or the middle point between point 2 and 3 as our moment location. So because the shear flow and therefore the shear force acts to that location, it will basically have no arm, therefore creates no moment. So by just looking at the image and the problem, you can reduce the complexity of the problem immediately. So if this was an exam question, you don't have to go blindly calculate all the shear flows and then determine the shear center. You can choose your location wisely and then calculate it, the corresponding components to that to solve the problem. So in this case, we say we're gonna choose the midpoint of 2, 3. So therefore, we don't need a shear flow in 2, 3. So we need the shear flow in 1, 2. And based on symmetry, we know that the shear flow in 3, 4 will be equal but opposite in sign. So we calculate the shear flows, 1, 2. And then we set up our moment equation. And in this case, the moment equation is equal to Sy multiplied by psi, which is the distance to the midpoint of 2, 3. And that must be equal to the shear flow, or the moment caused by the shear flow 1, 2, plus the moment caused in shear flow 3, 4. So shear flow, again, keep that in mind. That's basically the shear force per unit length. In order to get from shear flow to shear force, we have to basically multiply each of the locations by this corresponding ds, or the segment towards x. So if you want, in this case, what we do over a segment, we just take the integral. So from the segment 1, 2, we take the integral that's from 0 to b of shear flow Q1, 2, and this h over 2, that's the arm, moment arm from point 2 or to the midpoint of 2, 3. And we multiply by 2 because both shear flows, 1, 2 goes to the left, 3, 4 goes to the right. So both of them create a counterclockwise moment. So therefore, both of them are positive on the right hand side. So on the left hand side, the shear force in this Sy times I creates a counterclockwise moment. So that one is positive on the left hand side. So in this case, everything is positive. So if you do the calculation, then you get a value for psi. And if you look at this value for psi, so in this case, we have 3b squared over h multiplied by 1 plus 6b over h. So what we know is that this value is first of all finite and it's positive, indicating that it's basically outside of the cross section. So keep in mind that this shear center is basically just more mathematical definition. So if I had a cross section in real life, and if I applied the shear force outside of the cross section, but still some way somehow connected, so the load actually transfer, then that's the location where I get pure bending and no twisting. So we'll see that often, especially in closed and open sections, that the shear center will be, depending of course on the cross section type, will be outside of the shear cross section. And just keep in mind, if this was a real structure, you still had a transfer of loads. So this will be some way somehow connected to that location. So a couple more things. If you have If we have a closed section, say a wind box, and it's fully symmetric, then it will lay in the middle, because due to symmetry, the shear flow in this direction will be equal to left side, etc. So basically, they will contract. So if you have a double symmetry, it will lay on the intersection of the two symmetry planes. But say, for example, if you have a wind box and this side is thicker, then it will still lay on this axis of symmetry, but now you have to still determine which location, say from this midpoint center of the wind box, which location the shear force must act to create only a bending moment, or to create only bending. So just keep that in mind. And if it's a closed section, it will always lie within that closed section. So there are a couple of tricks you can do just to identify where the shear center lies and give it as a first check on your solution. Yes?
From a design perspective, we could just use the shear force and bending moment diagrams to design something. Why do it need the shear flow? Or how is it important as a design parameter, I guess?
Because if your shear flow is outside of your shear center, then you automatically know that the structure will also bend and twist. So if you're limited,
okay, so the simplified versions of the shear force and bending moment diagrams were very symmetric structures.
Yeah. So you can still get your shear force diagram. Say, for example, if you have a wing that's something like this. Say the top view, right? So this is our aircraft. This is our wind box or wing. We simplify it by saying, well, the wind box is a certain beam that lies here, right? So often, which will happen, and this one has a cross section like this. If you look at the lift, it often acts on your aerodynamic center, which, say, in this case, to simplify, coincides with your front spar. So now you have to take into effect that basically it's not on your shear center. So basically, you can bend and you can twist a bit. So you have to basically take that into account. If your design only allows for bending, then you have to come up with a solution for this.
Okay, so if the shear force is on the shear center, then you don't really need this shear flow and all these calculations. But if it's off the shear center,
so this is basically to determine where the shear center lies.
Yeah.
So it gives you an idea where I can apply my force, so I only get bending. So if it's in, so you know mathematically where you need to apply the force to have a bending. In most cases, you still have, say, for example, a wind box. You put it on the, say, front spar. So, but you take into account that the structure can basically lift up and twist a bit. But that's taken into account in your design. I need to know. So if you don't design for a twist, you might come up in issues later on. Say that's, so if your structure, in this case, it's free floating wind. But say if your internal component and you load it, it might hit a different component. So from a design perspective, you have to take it into account. From an analysis perspective, in some cases, this can be just seen as a mathematical construct. It's just saying, okay, I need to apply the force here, so in order to have this. But yeah, we will assume in most cases, for the shear flows, we really don't care where it lies in some cases. Yeah. Because we will just do the calculations because the location of the shear center doesn't affect your shear flows, the quantity of them, the flow direction or the magnitude. It doesn't affect those. It's just like affecting how the structure, if the structure bends or twists or just bends. Okay. So the next topic, we're basically going into closed sections. Again, say for example, we have this, the wind box we just had shown. So we compare it to our C section or our I section. So we said for an open section, these two are considered open, and this is considered closed, of course. So for the left-hand side, open section, we always said we're going to start a location where we know that the shear flows start at 0. So this will be if we give it numbers 1, 2, 3, 4. So in this case, we're going to start at 1 or 4. And in this case, 1, 2, 3, 4. In this case, we can start either at 1, 2, 3, 4. Let's call this 6 and 5. So you don't want to start at 0.5 or 6 here because there will be some values that you don't know the start point of it. So the question becomes clear, okay, well, where do I start for a closed section? So because in this location, since it's closed, we don't know where the starting point is and we cannot assume a 0 starting point. So what we do is we basically cut the structure open. So we say there's a cut, we make a cut here, small cut. And we say we have a closed structure is actually open structure and plus some correction to the cut we made. So now we can use our open shear flow equations to calculate the open section shear flows, and then we just have to basically compensate for a cut. And in this case, to put it a bit more correctly, so if we have a shear flow, Qs is our QB plus Q S0. So this is your open section shear flow. And this is your correction. The subscript B they often use for basic. So the question becomes now, okay, how do I calculate this? So in this, what we also say is like, okay, we have the open section, the QB, and then we have the correction. In this case, the correction shear flow that we apply basically is a constant shear flow. So we also know that the correction shear flow, QSB, is a constant value. Because we can make the cut anywhere. So normally it will be closed, so you continue shear flow. We now have made it open, and the correction to basically close it out, we have to add a constant shear flow to that, and that will be added to all the points in the structure, of course, not just a single point. So we know that this is a constant value. And with that in mind, we can basically start our derivations to see what this value is and how it relates to our cross section. So in this case, we use a generic cross section. We define some axis system. Our location is applied here. And let's see, this will be our location where we take this and for the moments around. Here, psi, and we have eta. And we can set up the same equation that we did before for the shear center determination. We can set it up again. In this case, since we take the most, generic case, we have both an Sy and Sx. So in this case, if you take the moments around the point in the cross section of interest, we say that, of course, Sx, this creates counterclockwise, this creates clockwise, so that's positive times negative, minus Sy psi is equal to all the shear flows of Qs multiplied by the arm Q P ds. And this shear flow in a closed section can be, of course, split up into the QB, PDS, plus, see, it's still visible, the integral of QS0 PDS. In this case, P is the moment arm, okay? So we said earlier that the shear flow, the correction shear flow, is a constant shear flow. So basically, it's independent of ds. So therefore, we can take it out of the integral sign. So we get is the QB PDS plus QS0, the integral of PDS. So we'll write it slightly. Again, this is our open shear flow sections that we calculated earlier. So we know what those values are, and we take it as a point of it. And this integral basically means you take the integral on the entire closed cross section, so the circumference of the complete cross section. So, okay, so we can focus currently only on this part, since this part is basically known. So if we would draw this segment of QDS somewhere on our cross section, let's draw it. Say we have a part that is QS0 there, and it's basically acting on a small incremental change. So let's look at that area. So this is basically tangential to it. So this is our QDS of QS0 on that small section. And this segment this RTS, and then of course the moment arm is always perpendicular, since we're talking about forces, so we have to find, this is basically a moment arm, so making sure it's perpendicular, so this is P. Okay. So, and we have the integral, which is, in this case, Qs0 of P ds, right? Where P is our moment arm. So, and then we do this for every segment. So, if we were to just look at one thing, it's basically the integral is the summation of all the different components. So, basically, integral is just nothing else than summation. So, if you look at one segment, this PDS, since this is the base of how it intersects with cross section, this is the height. You can see that is basically nothing else than an area equation of a triangular segment, right? So this PPDS, you can see that as, say, PDS is basically half an area, say delta S, area S, and that will be equal to this DAS. Does this make sense, what I said here? So we know if you want to calculate the area of a triangle, it's the base times the height. So the area of a triangle is 1/2 base height. And if the triangle is slightly deformed, you still have this base, and then this is the height. So basically, that's what we apply here as well. So we can use this principle to determine what this integral is. Okay, so as a side note, so we can say that the area dA half is on this side is equal to the area. So now we can basically form this integral is basically the summation of all those small areas. So the integral of dA is equal to the integral of PDS half PDS. And then if you take the A on this side, so if you take the integral of all the areas, segments, what you get is the total area. So if we evaluate the full integral on this side and take the half to the left side, we say get the following thing, PDS. So we know that the integral of the moment arm over all the sections is equal to twice the area. Now we can use this in combination with this function to write that QB PDS plus 2 times the area, enclosed area, times QS0. Because QS0 is constant, it's not a function of ds, so we can take that as the integral. And then we can look at the cross section and we can determine that the integral of PDS, the moment arm with respect to the segment, is equal to 2 times the enclosed area of that cross section. And then we can use that to determine substitute back into our moment equivalence equation here to define that how we can find the correction shear flow. Because now on this side of the equation, if we look at it, the shear forces are given. The location where you take your moment around is basically up to you. Always choose the most convenient location where most of the shear flows goes through, or you intersect with most of your shear forces. So in this case, a good position to locate is actually located here, because then this left-hand side of the equation becomes 0, right? QB, that's the open section shear flows. So you already calculate that using the open section shear flow equations. So now this is known. QB, the integral, just evaluating the integral, is also known. And then the only unknown here is left over is QS0. So now you can use the basically the shear flow equation or the shear center equation, and you can choose a convenient location and where you know the answers, say for example at the location where both shear forces interact or go through, to create a left hand side is equal to 0, and now you have one equation with one unknown, and you can solve for that correction shear flow. Does that make sense? Yeah. So let's see. Yeah, we do an example. Okay. Let's go through these steps with an example. I think that's the easy way to go forward. So let me recap very quickly. So we have a closed section. So step 1, make a cut. Step 2 is solve the open section. Step 3 is set up a moment equation. And step 4 is solve moment equation for as 0, your correction shear flow. That's basically the 4 steps that you have to take for every closed section. Okay. So we have the following cross section. It's a closed section. It's a point box, say a box with a cone on top on one side. So the shear force acting on a front spar, and this is our x-axis, and this also our y-axis, and this is radius r. The thickness is t everywhere, and we define 1.1, 0.2, 0.3, 0.4, 0.5. So what we have no as x given, and we also know that it's symmetric, so ixy is equal to 0. That's what we already get. So our shear flow becomes minus sy over ixx, the integral of 0 to s of ty ds plus qs0, which is our correction shear flow. So now what we have to do is to make a cut. So where would you make a cut in this location, in this cross section? Yes, that's perfect. You always want to make a cut, and which reduces the problem a bit. So if you make it around a symmetric point of view, a symmetric axis, it basically reduces your problem to half the problem. So you can calculate, say if you make it at point 1, you can calculate 1, 2, 2, 3, and 3 midpoints, say let's call this 6, and the rest will fall out from symmetry. So, and then you can also choose, okay, the correct answer is definitely in location x, or along the x-axis. And then the second question is, where do we make this? By the way, this is not a beam. Sorry, just like this. That's just the coordinate of the y axis. You see here. So the question becomes, okay, do I make the cut in my location 1 or say location 6? And either is fine. The only thing I would say in this case, make it in one. Just once you do the shear flow equations and moment equivalence equation, it can become a bit simpler. Actually, but actually in this case, it doesn't really matter. No, in this case, it doesn't really matter. So in this case, you can actually make it either 1 and 6. I was thinking maybe you can ignore this part, but you cannot ignore it. So we make the cut in 1. So we make the cut in 1. So basically, this reduces the problem for an open shear flow problem. And then we just kind of solve that first, and then we come back and add a correction to it. So let's do the open shear flow. So Q as consistent, QB12. By the way, the moment of inertia in this problem is given as IXX is equal to 6.24 TR cubed. So we're going to use that, okay? So for 1, 2, since basically doing this is theta, so we have to do the coordinate transformation. So instead of 0 to s, the path s is basically from 0 to theta. So we get minus sy ixx, then 0 to theta, and then the t remains the t, and the y coordinate becomes r sine theta, and our dy becomes r d theta. So if we 1 over 6 is 0.16, and if we evaluate this integral, we get 0.16 sy over r minus 0.16, by the way. Is that correct? No, because the minus drops with the cosine. Yeah. And then we get this becomes cosine theta, evaluated at 0, and of course 2 theta, which becomes 0.16 sy over r, and then cosine theta minus 1.
So if we were to make the cut at 6, we would use x and y instead of the r's?
No, you still have to do a quadratic transformation where you go from 5 to 1, or from 5 to 2, depends on how you do it. So whenever you have an arc, you want to do a coordinate transformation, but you just have to do that coordinate transformation at the arc segment. You don't want to do the coordinate transformation. It doesn't make sense to do it at a straight line, because then you just make your life more difficult. So when you have an arc, you do a coordinate transformation, and when you don't have an arc, you stick to your x and y's. So this is the shear flow, how it basically behaves from 1 to 2. And of course, once we get to 0.2, we have to know the start value for our segment in 2, 3. So we want to evaluate this QB12 at 0.2. So if we evaluate QB at 0.2, it's equal to QB of 1, 2, and the theta, in this case, equals to 90 degrees, which equals to pi over 2. So pi over 2. So you plug this into this equation, and then you can get your, because pi over 2 becomes 0, so you get minus 0.016 sy over r. So that's our shear flow value at 0.2. So now we go calculate point QB23. We again use the same principle, so we can reuse this segment. Get 0.16 sy over r. And then, what we get is the integral is 0 to s dy ds The y location remains constant, so it's not a function of s because it remains constant. So, and that equals to, we have the couple of quarters, so this is equal to 2r. So y is equal to r. Can someone plug in what 1 over 6.24 is? Can someone do that quickly, actually? And double check something. Yeah, 0.16. Yeah. So that's correct here. Let me see. 0.16. Let's be a bit more accurate. Let's call this TR cubed from the IXX. So we know that, of course, the T's cancel, so we can get rid of those. And we know that Y was equal to R. R doesn't change, with Y location doesn't change with S. So this cancels with one of these. So we get 0.16 SY over R squared, 0 ds. And this becomes basically 0.16 SY R squared S, and S goes from 0 to 2R.
So what happened to T again?
Oh, we have here, so this segment we have SY IXX, right? So we have SY 6.24 TR.
Okay, I see it. I got it.
So that, I just wiped it out. So that canceled with the T that was here.
That makes sense.
And then, since Y was equal to R, I canceled that R out here as well. And now we can evaluate this integral, so it becomes basically, 0 to S, and we still have to actually add 0.16 SY over R to it as well. That's the QP at starting location point 2, so you cannot forget this one. So let's do it a bit more cleanly. So plus 0.16 SY R. That will be the equation. And then, of course, what we can do is we can take 0.16 out because it's a bit easier, and we can combine those two equations. And what we get is 0.16 SY R squared negative. And then what we get is, if we evaluate this integral, this becomes S1 plus R. And the reason why is this plus, not 1, but plus R is because we took the R squared here out of it. So in order to calculate this, we basically becomes R instead of 1. Yes?
So the idea was to find the Q of some segment and then add the Q of the previous one.
Yeah, you always have to add a start point to it.
Yeah.
That's the reason why we start with the location where it's 0, because we know the start to be 0.
So the value of QB12 is 0.16 SY over R cos theta minus 1.
Yeah.
So, and did we plug in the pi over 2 in it?
So there are two shear flows. So this is the shear flow equation at the segment.
Yeah.
And this is the shear flow value at the point.
Okay.
So for example, if you're interested at 45 degrees, you plug in pi over 4, and then you get your shear flow at, say, the midpoint of 1, 2. Because we want to evaluate point 2, because that's the start point for segment 2, 3. So we determine the shear flow segment equation, which is basically still a function of, in this case, theta, and in this case, S1. And then, before we can continue to segment 2, we have to evaluate this at segment 2 in order to find this start point here. And now we evaluate from QP3, we evaluate that at point 3, so it's equal to QP23 at S is equal to 2R, in order to find the start point for segment 3, 4. So if we evaluate this at 2r, we get 3r here. So this becomes just over r, and this multiplied by 3. So we get 0.48. Yeah, so Q3 becomes 0.48 SY over R. And then we use this as a start point for sigma segment 3, 4. So if you do the equation for 3, 4, we have QP3, 4. We basically get, let's start with that, just write that up front, 0.48 SY over R, that was our start point, plus our standard equation, which becomes 0.16 SY TR cubed, and then the integral of 0 to S TY ds. And in this case, if we move along our segment, the Y location changes, so this is no longer a constant.
Should it not be negative 0.16 SY over R in the...
Yeah, it should be negative. Yeah, that's negative.
All the way up? In the 2, 3 as well?
This is already negative here. Oh, no, this was segment 2. So segment 2 is negative, yeah. Yeah, negative here.
In the bracket.
Yeah, this is here what negative takes account for.
Yeah.
So there remains positive. Let me see. Yeah. Yeah, that's correct. Negative sign. So now we have to determine what our equation for y is, and we can determine y for 2, 3. Again, like the same point. So at start point 3 is equal to r. At location 4 is equal to minus r. So our equation becomes r minus s. This S3, where S3 goes from 0 to 2R. Does this one make sense as well? Okay, so now you can plug this in. So the t's cancel out again, and we get, what do we say? We have R minus S3 ds. So if we evaluate that integral, we get Rs minus S over 2 squared.
So the R and the negative R, those come from the 2R, right? The upper portion of 2R being positive R and the bottom portion of 2R being negative R?
Yeah. So you just have to look at the y coordinate of this point. So this is 2r, so it goes from 0, this is 1r up, and we go all the way to 0.4, so we go to negative r. So we know we go from r to negative r, and we travel 2r. So if you plug in s3 is equal to 0, we get r. If you plug in s3 equal to 2r, so the total distance traveled, it equals to negative r. So y at 0.3 is equal to r, y at 0.4 is equal to negative r, and the s that we travel, 0.3, is a total of 2r from 3 to 4. So our y equation becomes r minus s3. And if you evaluate that, all those segments are conditions are met. Okay. And of course, we can evaluate at 0.4. And based on symmetry, we could also immediately say this is the same as 0.3. So let's rewrite this a bit to get a bit more nicer equation out of it. So we will get as, let's take 0.16 out of it. 0.16 SYR. And then we have RS minus half. So RS minus half S. Oh, sorry. RS minus half S plus 3R squared. And the reason why it's 3R squared is, again, here we have R cubed, and here we had R, so basically have to have an R squared in order to get that, satisfy that equation. And we multiply by 3 because 0.48 is 3 times 0.16. So this is our shear flow equation for segment 3-4. And we don't have to calculate segment 5-4 because symmetry of 2-3. We don't have to calculate 5-1 because it has symmetry of 1-2. So what we now have is all the open sections, shear flows. But we still, so we made a cut, so this is check. We solved the open section shear flow. So we now have to set up the equation and we have to calculate the correction shear flow. So let's do this. So this is 2R. This is 2R as well. Yeah. And we have our shear force acting to that segment. So I'm gonna see where's the large space. Okay, I have some space here. Yeah. So we calculated earlier QB2. We said that's negative. No, that's 0.16. Negative 0.16 SY over R. QB3 was negative 0.48 SY over R. And then point QB4 is negative 0.48 SY over R for symmetry. QB5 is negative 0.16 SY over R. So we could have evaluated the 0.6 as well. That's basically the midsection between 3, 4 by just plugging in this equation S is equal to R. So if you want to calculate the midpoint, so QB6 is basically the midpoint between these two. And if you evaluate that, you get negative 0.56 SY over R. So let's keep that there, okay? So now what we do is we set up the equation and we calculate the correction shear flow. So we set up the moment equation. So we want to make things easy for ourselves. So the location that we pick up for the moment equation, in this case, will be this location here where our origin of our axis system is. So basically SY doesn't have any moment arm, so basically that part is 0. And then we look at the shear flows and what moments they cause. So we know this is QB23. This is QB12, and this is QB34. So the moment arm of QB12 is in function of theta. The moment arm of QB23 is just R, and the moment arm of QB34 is 2R. So let's set up the equation, and of course we can use symmetry, so we can multiply this by 2 and this by 2 and keep this as 1. Okay. So the moment arm will vary for segment 1, 2, from 0 to pi over 2, and that will be equal to QB12 R squared theta, because that will be basically R multiplied by RT theta, so R squared theta, plus 0 to 2R, that's the distance that we travel for QB23, so QB23. So we go from shear flow we integrate it over the distance we travel, we get a shear force, and now we multiply by the arm, so which is R to get the moment. And then we also do, we take the integral of 0 to 2R. That's how Q3-4 travels, the total distance. So again, QB34. So we went from QB34 from a shear flow, we integrate over the distance it travels to shear force, and we multiply by the moment arm, in this case is equal to 2R, and we get that moment contribution to it.
So is that an added or is that a separate equation?
Oh, no, this is added, sorry. Also, you don't see it on the screen, so that's the reason why I go down. So what do we know? So for actually, in this case, we also have to add this section and 5-1 as well. But as due to symmetry, we can just put a bracket over here, and we say we multiply this segment by 2. Okay? So that takes account QB45 and 5-1. Another quick thing that reminds me, the index notation, the subscripts, indicate the shear flow direction as well. So when you have a negative shear flow, it basically means it goes in the opposite direction. Okay? So once since we got a basically negative shear flow, it basically means instead of going clockwise, we're going counterclockwise. Just that's what it means. Good. And now we have to add the correction shear flow to it, but we already know that that's equal to 2 times the enclosed area times the correction shear flow QS0. So you can abbreviate this with QC, QS0, Q0, multiple things exist. So we have to now calculate what the enclosed area is. So the enclosed area is 2R times 2R, so you have this box, plus the area of this half circle. So we get 4R squared from 2R plus times 2R, so that's this box here. And then we multiply by that. The area of a circle is pi r squared. We have a half circle, so we divide by 2.
So is that just in front of the 0 pi over 2 and 0 2R for QB12 and QB23?
Yes. And the reason for that is, so I think in Maxim what he does, he defines 0.6 as well. That's the reason why I defined it here. And he calculates instead of segment 3.4, he calculates segment 3.6, and then he uses this whole equation times 2. Because now you can say, I have a full symmetric point. What I did is I used symmetry for 1, 2, and 2, 3. I calculate this as SS, and then use the symmetry for 4, 5, and 1, 1, 5. So QB12 symmetric is the same as 1, 5, and 2, 3 is the same as 4, 5. And this one, because I go from 0 to 2R, I keep that as one equation.
Could you explain the R squared d theta?
Yeah, so you basically have to define this arc length. So that's going from 0 to basically that goes, the length for that is R d theta, right? And then you have the moment arm, which is R in this case. So you get R squared theta, d theta. So now we plug in this equation, the enclosed area here. So we say that we have 2 times 4R squared plus pi R squared over 2 QS0. So as stated before, the equation for 1, 2 is given here. The equation for 2, 3 is given here. And the equation for 3, 4 is given here. This one is it. This is part of this integral. So now you evaluate the integral separately, and you have basically known value, just a numerical value, numerical value, numerical value, numerical value, and one unknown. So now you can solve for Q as 0. Q as 0 is equal to 0.23 SY over R. Okay. And now your final answer would be adding this to all of these segments. So you would have to add QS0 here. So plus, let's just call QS0. It's easier. This would be your final solution. Because this was all the open sections. We have a constant correction shear flow, and we add this to our shear flows locations to get the final answer to it. So let's go to the slides, and we can go through that example as well. Okay. So yeah, this was what we said how we solve a closed section. So we basically make a cut. Once we make a cut, we can solve the open shear flow sections, and then we have to correct that presence of a cut in order to have to close it again. And in that case, we basically defined a correction shear flow, and we defined that the correction shear flow basically equals 2 times the enclosed area. So now if you go inside, if you find the moment where you take the center, or the location where you take the moment equation from, we always choose it wisely. You can always reduce the complexity of your problem a bit. So by choosing the correct location, in this case, we coincide with the location of the lines of action of the shear forces. So that was equal to 0. So and we calculate the correction shear flow based on that. So this was the example. We made it. We said let's take the cut location at the axis of symmetry to reduce the computations. So we did all the open shear flow sections. So 412, 423, and 434. We came up with 3 equations for QB12, QB23, and QB34. Since that's only needed, all those are needed to get a shear flows in the entire cross section. Once we did that, we set up the equation to determine the correction shear flow. And in this case, we take the equation around this point of origin. This interacts with the line of action of our shear force. So the shear force multiplied by the moment arm is equal to 0. Or the shear force doesn't have a moment arm, so the moment created by the shear force is equal to 0. So that's what we see 0 on this side. And in this case, we take the integral from 0 to pi over 2. That's this arc length from 1 to 2. Then we take the integral, the contributions from QB23 from 0 to R. And in this case, QB34 is within the brackets multiplied by 2. And the reason for that is the integral is only taken from 0 to R. So what I did on the board, I took the integral from 0 to 2R, so entire section over from 3, 4. And with this maximum does, he takes it only from 3 to halfway the point, so he takes the integral from 0 to R. And that's the reason why this is inside of the 2 is inside, that this part is inside the bracket of 2. And then the enclosed area, which is 4R squared, plus pi r squared over 2 multiplied by q as 0. And then you can solve this equation to get the correction shear flow equal to 0.232 SY over R.
So we determined that the shear center is at the origin of the axis we had before? Or like, do we already know the shear center?
You don't know the shear center. So we in this, so the shear center we calculate when we ask basically for it. So in this case, in this case, we can go and basically calculate it. Let me see.
So we just needed the moment would equal 0 at that location. So
Yeah.
that's why we're able to do it. We didn't need to actually know where it was.
No.
Okay.
So what we do in this case, we take a moment equivalence study, equivalence for location that we know the moment's around.
Right.
So you could have picked point 1, 2, 3, or 4. It doesn't really matter. The only difficulty that it becomes is how do you find the moment arm for say segment 5-1. So you want to pick somewhere which is convenient. And if you take it at the origin, then the moment arm for segment 5-1 and 1-2 becomes R, and that coincides with the location of our shear force, so the shear force disappears. And then once we calculated the correction shear flow, we can basically sum what we have. We know our correction shear flow is 0.36, and we have the shear flows 1, 2, 3, 2, 3, and 3, 4 as is. And then we can evaluate that point at each point. So we get those values. And like I said earlier, the negative sign basically indicates the direction of the shear flow. So as you can see here, you go at one point you basically switch signs or direction of the shear flow. That doesn't represent anything else other than just the directionality. So there's no such thing as a negative shear flow. It's this definition of your directionality is in the opposite direction that you assumed. Okay, I think there's a good segment to stop. I think we have one more segment left. Let me check actually. Yeah. Yeah, let's continue actually. So we have 5 more minutes. I will just introduce the topic and then show you an example. I will recommend you to do that at home. We can start the example next week, and then we go back to the torsion section of it. So of course we have an aircraft. We don't have just open. We don't have just closed. We have combinations open section and open section and closed sections. So the question becomes like, how do we analyze those combined sections? And what we do is basically we combine the 2 approaches that we talked about. So we calculate the shear flows at the open sections. So in this example, for example, we start at 0.1 or 0.8, sorry. We calculate the open sections, and then we see that we have a box that is defined by 0.3, 4, 5, and 6, right? So the next step is, okay, we have to basically make a cut in that box and treat that again as an open section. So we make, for example, a cut at at 0.0. You treat the box 3, 4, 5, 6 as an open box. So now you can calculate the open shear flow section of 0 to 3, from 3 to 4, and from 4 to 9 in this case. And then you can use symmetry to calculate all the other ones. So key point is now segment is actually 0.3, because now you have a shear flow coming in from the left and a shear flow coming in from the right. So before you can calculate 0.34, you have to know where the shear flow is due to the contribution coming in from the left, so segment 2-3, and you need to know where the shear flow contribution is from coming in from the right, which is segment 0-3. So in this case, what you would do is you calculate the open shear flow section at 1. You go from 1 to 2. You calculate a shear flow at 2.2 is. You go to 3, and then you restart. You make a cut at 0. You calculate, since this is now an open section, the start point at location O, location 0 is 0. So you calculate the shear flow from 0 to 3, and you determine what the shear flow is at 0.3 is. And then before you go into segment 3-4, you add, instead of just the segment of Q3 of the left hand side, you also add the Q3 coming in from the right hand side. So that's only other point that you have to take into account. If you have an intersection, where two shear flows come in from multiple directions, you first have to calculate all the shear flows coming in before you can calculate the next segment. So this is actually a very good example. It forces you to determine the center of gravity and moment of inertia, and it's an open section, closed section combination. So I'll advise you guys to do this at home, and then next week what we do is we go through this example in a relatively faster pace, and then we go revisit back torsion. And once we complete the torsion, we do a couple of, say, one lecture of just doing examples, maybe 2 lectures, and then I will give you the second in-class exam, which will again be in online. And I think at this time I will give you guys 48 hours. Just post online on what is it? Saturday morning, and then deadline will be Monday morning, something like that. Okay, and it will be again three questions targeting both shear, shear forces and shear flows and torsion. Okay, perfect. Are there any questions regarding the closed section topic that we discussed? No? Okay, perfect. Thank you, and see you guys next week.